Okay, we're happy to have our very own Nemanja Kaloper, who's going to tell us about a quantum mechanical mechanism for reducing the cosmological constant.
Let me just do this one thing. Okay, there we go. Hopefully that's it. So I'm going to tell you about a couple of papers I've written recently, and the last one in collaboration with my friend Alex Westphal from Germany. You see the references down at the bottom of the screen. I think I'm going to provide John a copy of this, so you can actually, you don't have to write them down. You can just, access it from there. What this is about is the following. I'm actually, with regret, not going to claim that I've solved the cosmological constant problem. Okay, I might have, based on the results here, I might have made this claim in 1996. Before it became, before it became, the word evident is a bit too strong, but let's say before the experiments indicated that the universe is accelerating. So what I'm going to do is, I'm not going to be able to say to you, I'll speculate and I will throw a few ideas around and so on, but I'm not going to be able to tell you what drives the cosmic acceleration now. Okay, I'm going to make an argument that it, however, is most likely not a cosmological constant, which in itself is fine. Okay, but if this argument, I think the argument is correct. If this argument is operational, then in fact, actually, what I'm going to do is argue basically that there are two things at play here that you should draw as a conclusion, which is that the Sitter space is unstable. It decays in an appropriately extended formulation of general relativity. Okay, it decays gradually in steps, and that Minkowski space or vanishingly small cosmological constant is a quantum dynamical attractor of this evolution. Okay, so that's the claim in a nutshell. Okay, and so let's kind of run along and see how that comes into being. Provided I can scroll these things, and for some reason I don't seem to be able to do that. See, I told you, Pauli syndrome kicks again. For some reason doesn't seem to be. It's supposed to be good. This is completely stuck. I'll just do it manually, okay? Not to take any more chances and avoid any further delay. So let's start with a brief overview, okay? The idea is basically, I'm going to give you an argument. There is a simple and straightforward way to actually extend general relativity by adding new degrees of freedom, discrete degrees of freedom, okay? In a way, actually, perhaps it's better to say that gravity has those degrees of freedom built in. They're latently present in the theory. You just need to tickle the theory in the right way for these degrees of freedom to reveal themselves. Okay? These degrees of freedom persist in the far infrared. Okay? And they do change the evolution in interesting ways. So to identify these degrees of freedom, okay, in the process of discovering what they are, you actually find out that this extension of, let's call it general relativity on a multiverse of sorts, on a metaverse, okay, you find new symmetries, okay? If you want to interpret these new symmetries as gauge symmetries, which you probably should if you want to have them have a fighting chance of surviving predations of quantum gravity and not be broken in some bad way, okay? what you need to do is to quantize the theory and introduce these gauge symmetries as a redundancy. In the semi-classical limit, where I will be exploring this theory, that simply means adding charge. Because these gauge symmetries are associated with rank 3 potentials as opposed to standard rank 1 potentials, their charges are membrane. So I'll be adding certain gauge fields, which are described by 4-form field strengths, and the corresponding towers of membranes with tensions. Okay? The fluxes that are sourced by these charges and their subsequent discharge via what's completely analogous to Schwinger charge, Schwinger discharge, Schwinger particle production in background fields, yields this kind of a simple GR-only version of landscape. Okay? But in this landscape, it'll turn out that in order to have a way of addressing the cosmological constant problem, I'm not gonna need, there is a limit, there is a regime of the theory, okay, within which you can address the cosmological constant problem without deploying anthropics. Okay, I will also make comments regarding other, okay, similar looking, okay, ways of discharging away the cosmological constant via emission of membranes that do employ anthropics, and I will tell you what the difference is. So here are the hidden degrees. Here is how you find the hidden degrees of freedom. In some sense, you know, it could have been done in 1915, in that, you know, miraculous month of November when Einstein wrote 4 papers, and of course Hilbert wrote the one, and led to us to formulate the action principle for general relativity, and, you know, led to all the stuff afterwards and so on. Here is the thing in a nutshell. There is this usual textbook statement we all make when we're teaching GR or, you know, studying it, we notice it. I've made this statement, you know, a billion times probably, without too much exaggeration and so on, which is that the measure for general relativity is unique. You know, you write down d for x root g, you take the Ricci scalar, you multiply, you integrate, you have a covariant theory, and you're happy. The fact is, this is not true, okay? The measure for general relativity for theory of gravity that is covariant, satisfies all the usual rules and requirements, is not unique, okay? Instead of d for x root g, you can take any 4-form f. Literally any 4-form will work just fine, okay? In fact, they find that f with some wisdom after the fact to be a field strength associated with the gauge potential, which is a rank 3 form, okay? And write this in the action, and this works fine. In fact, in 4 dimensions, by antisymmetry of the 4 forms, okay, f has to be proportional to the usual measure root g d for x, because this is the only unique, you know, the 4 form that you have. It's basically root g d for x is a basis, okay, in the space of 4 forms in 4 dimensions by antisymmetry, okay. But actually, this also shows you that this measure written in this way, okay, as an arbitrary generalization of the standard Riemannian measure, okay, actually won't lead to a theory which is GR alone, okay, because of the fact that the ratio of the 4 form to the standard root g d for x is in fact a completely arbitrary scalar, okay. So actually, if you just took Einstein's general relativity, Einstein-Hilbert general relativity, and replaced root g r by fr, okay, you wouldn't get GR, simple GR alone. You would actually get a Browns-Dicke theory with a Browns-Dicke scalar phi and an extra integration constant, but never mind that for the moment, okay. And that is characterized by that coupling parameter of Browns-Dicke, that thing W that is equal to 0. But that's okay. The theory will still have kinetic terms for the scalar that would arise from mixing with gravity and so on and so forth. And indeed, this would just be the, you know, a Browns-Dicke thing. Here in this talk, because I'm interested in the simplest incarnation of this generalization of GR, okay, I don't want that. I'm going to get rid of this scalar by projecting out its local fluctuations and adding in the extra term that's going to guarantee that the scalar is a constant. Okay, that extra term comes after I introduce one more 4-form field strength, one more three potential, okay, G and B. And this bilinear term, don't worry about these factors, -1 and 4 factorial, blah, blah, that's just normalization coming in from permuting indices and so on. Okay, that you can always fix even if you didn't know that you needed them, all right? And when you actually stick this term in, notice, of course, that you can kind of commute these. You can by just working through with, you know, the using antisymmetry of form of inner product of forms and so wedge product of forms, not inner product, wedge product of forms and so on. You can pull these through and you can rewrite this as G times epsilon F with indices on F and so on and so forth. That's useful for writing down equations. Bottom line, what I want to do is I want to consider a theory which generalizes GR, where I replace the standard Einstein-Hilbert term by this piece here. Okay, this generalizes the measure, and this term ensures that there is no additional scale of degrees of freedom, and that this theory only contains the standard local fluctuations to GR, namely the two massless helicity 2 tensors. So I claim this is just GR, and you might doubt it at first sight because this doesn't quite look like the right structures. But I'll alert you to the fact that this is still generally covariant. And this still, because the general covariance has to satisfy the local form of general covariance, which is Bianchi identities. And these Bianchi identities is essentially what controls what sort of, you know, wiggling things in your theory you have. And so let's prove that this is true.
Sorry, our question. The term you're adding on, is it a total derivative?
No.
It's not.
No. And I'll tell you later how you can think about where that term comes from and why it's there after we dualize this theory using a canonical transformation. So remember the question.
Okay.
Ask it again later,
Okay.
because it's actually an interesting question.
What if you add a source for B?
I will charges. Okay. As long as I add membrane charges, the only thing that will change is that certain quantities, but let's wait again, you know, we'll discuss that in more detail, but certain quantities that are otherwise just constants actually would not be constants globally because they can jump on membrane walls. Okay. If I add an arbitrary source, then of course that will change the story in a more dramatic ways. But right now I'm not interested in doing that. And also I'm in principle protected from needing to worry about that by gauge theorem. So let's prove that this is indeed just GR. To do that, we just go, you know, we follow the simplest possible road, which is vary the action. So actually to do that, let me go back, previous slide. And let's just do one of the variations in real time because it's easy. The dynamical degrees of freedom are the metric and the three forms A and B. We vary with respect to them. So if you, but A only appears in here, covered under the derivative. So if you vary this with respect to with A, the Euler-Lagrange equation you obtain is a variation of A times derivative of this thing in parentheses equal to 0. Because the thing in parentheses is a scalar. You can integrate that equation immediately, okay? And this is what I've done here, okay? The notation which I'm employing is actually again coming in with wisdom after the fact, because I will a posteriori learn that these are just the right quantities. And I'm kind of, you know, being prescient about this of sorts by introducing the names, naming them in what will turn out to be the right way. Similarly, the variation with respect to B produces another equation which tells me that the derivative of this is 0. Again, this is pure scalar. Okay, I can integrate it and get another integration constant. Those integration constants would be constants if I introduce those sources. And when I do introduce the sources in form of delta function localized charges, these things will jump on the charge. Just like the electric field or magnetic field jump in plain old electromagnetism if you introduce, you know, in the classical limit an electron or a molecule. Except they have a different rank. Finally, I go to the final, to the equation which I get by varying with respect to the metric. And that variation is a bit nastier because of these, additional things and so on floating around. But to simplify, I can use these equations in the process of deriving this variation, okay? And out comes this. And at first sight, it doesn't look like Einstein's equation. Because, it has this mass multiplying the thing. I mean, this looks right, and this looks right, and these two don't. Okay? But then you recall that you actually have the equations, okay, that arose from varying with respect to A and B, that you can use to simplify what you have here. In particular, you see that this term is just a constant, the integration constant, and this term can be eliminated using the second constraint to recover the missing piece R over 2, okay, that Einstein and Hilbert had, plus an extra integration constant. And lo and behold, when you eliminate these two pieces using these equations, your equations of motion are used to this. So on shell, the theory is in fact just GR. The theory has identical to solutions to GR. Except actually that's not quite true, okay? It's not one GR. Locally, this set of equations describes infinitely many GR because of the fact that kappa and lambda are integration constants. In fact, what this does, for those who may know these things, this is a generalization of what's called, and I like to call it, unimodular formulation of general relativity. Okay? I don't like to make distinction between unimodular general relativity and general relativity because there is no difference. If you properly think about general relativity, it's a unimodular theory because of the fact that it needs a counter term that cancels the UV divergence of the cosmological constant and leaves you with a finite part which is not calculable, which is instead appearing as a cosmological constant until you fix it with a measurement. That's this piece. Okay, but now on top of it, I have one more piece. The Planck scale itself, which is an integration constant. So in a classical limit, okay, this actually tells you that you have basically infinitely many universes that are following their own, wall volume history without mixing with each other. Described, each characterized by different values of kappa and lambda. If you like, actually, to me, what seems to be a near perfect analogy is with fluid flow, okay? This limit of the theory is analogous to laminar fluid flow. We have field lines, okay, or rather fluid lines, streamlines in a moving fluid that move smoothly, okay, right next to each other, characterized by some conserved quantity which tells you which trajectory you're on, okay, carrying you along and never intersecting until that is you hit some sort of impurity or you hit some kind of a nonlinear contamination of the fluid flow that generates turbulence. And then these lines start getting messy and there's going to be a little whirlwind forming in and maelstrom maybe in the end and so on and so forth. So the point is at this limit, in this classical, purely classical limit, okay, think of this as undisturbed fluid flow, infinitely many universes characterized by kappa and lambda. For now, they don't mix. However, consider now a field theory that sources that sits in that PMU which sources the geometry, okay, which, for example, suffers through a phase transition, and its vacuum energy jumps. And if its vacuum energy jumps, then actually what happens is that net cosmological constant, which is given by integration constant plus the physical contribution from the matter sector changes. So that basically means that suddenly your fluid line, okay, in that analogy with laminar flow, okay, the flow ceases to be laminar. There is going to be a shift. So one trajectory goes up to a point where phase transition happens, and it jumps and transforms to another trajectory, upon which the cosmological constant in the future, or the parameter analogous to cosmological constant, is actually different. So this tells you that you may be able to explore these and simply see what happens. And to do this, the simplest way to step up is to actually produce sources that can change these gauge field strength. Okay, as John was asking, in principle, what you do is you add charge. I mean, these are completely analogous to their generalizations, if you wish, to the case of lower codimension of charged particles in electromagnetism. These are masses, okay, or in this case, actually tensions, because we are dealing with codimension one object, right? Masses per unit area. And these are charges of these membranes, okay? And you add another tower just like this for the other gauge field that you have in the tube, okay? So in principle, these will end up changing the value of lambda, okay, in discrete steps, which are fixed because these are quantized, okay? And these will end up changing the value of the Planck scale, again in fixed steps, because they're quantized.
So what's quantizing it is the fact you're driven by a phase transition. So it's a
Well,
step.
for example, in fact, let me wait till later, and I'll tell you what I actually think. Let's put it this way: you can let me just give you a kind of a brief preview. You may think of these as quote unquote fundamental membranes. In some theory, I don't know whether such a theory exists, or you know whether there is a known UV completion of some supergravity, whatever, you know, which would give you, you know, the system of charges that source these terms with bilinear mixings and so on and so forth. You certainly have those when you have the standard F-square type gauge field strength in the action. Okay, and then of course these would be, you know, the charges and tensions of things that were, for example, explored back in the day by Brown and Teitelbaum and so on and so forth by many other people subsequently. Okay, or they can be emergent. Okay, I personally right now want to explore the possibility that they're emergent in the sense that actually, if I, you know, finish in time, hopefully, I might give you just a comment, okay, that I would like to think of these as basically, okay, generalizations of, okay, some non-trivial gauge theories in strong coupling with non-trivial topological sectors, where some of the duals of these charges are actually analogs of the strong CP theta parameter, okay, and the four forms, okay, are in fact actually topological structures built out of trace FF star, where F is the standard SUN gauge field and so on, okay? But let's not, you know, I don't have enough material to substantiate that quite as yet. That's very much work in progress. So now, having motivated the theory, you know, I could now continue and analyze that theory with those four forms and all those indices and so on and so forth, but actually there is a simpler way to do that. The indices are never found. Okay, whenever I'm manipulating indices, I catch myself making mistakes. So at least for particle point of view, okay, what I can do is I can actually perform a dualization of the theory and get rid of the electric field degrees of freedom and replace them by their dual magnetic field. In the case of Maxwell U1, that basically amounts to performing a transformation of E go to B and B go to minus E. Okay, in this particular case, actually, for four forms, the electric and magnetic duals are actually not distinctive subsectors of the gauge field because there is only 1 degree of freedom by antisymmetry. Okay, but nevertheless, what I'm really doing here, let me just give you an intuitive analogy of this. In the canonical sense, you know, you can go and you can dust off your Goldstein, okay, and go to whatever chapter 10, 11, I don't remember, canonical transformations, okay. And what this is just a canonical transformation. Here is the simplest example. Take a harmonic oscillator. Hamiltonian is Q squared plus P squared. Okay, the commutation relation is QP equals I, right? Okay, great. What's Q and what's P? So you will say, well, that's obvious. Q is Q and P is P. Then I tell you no, because now I'm going to replace Q by P and P by minus Q. And I have preserved by that transformation the form of the Hamiltonian and also the symplectic structure of the commutator. Doesn't matter which one I use, okay? So in this particular case, what I do the same thing, okay? The way to do it is actually to go to what's called the first order formulation of the relationship between F and A, okay? Enforcing that F is equal to dA and G is equal to dP by a Lagrange multiplier. Writing this transformation, writing this step in terms of the path integral by basically declaring the Lagrange multiplier, enforcing the definition of gauge field strength is to be also treated as an independent degree of freedom to be integrated over. If you integrate over P and PA and PB, this will give you functional delta function, which when you integrate enforces F equals dA. Okay. However, you don't need to integrate out these first. You can choose a different order of integration, and that choice performs effectively the canonical transformation. So here what I do is I complete the stress in the theory and leave these as the residual dynamical degrees of freedom that I will use to study what happens with the theory and integrate out these two. Okay. And when I do that, I actually get the effective action that looks like this. Okay.
So here the reality doesn't couple.
The pure bulk gravitational action now looks identical to the GR formulation, canonical GR formulation, with one exception. Kappa square and lambda are still to be treated as independent degrees of freedom to be varied over. Okay, they are constant officially only on shell. You should treat them. They're just what kappa and lambda are. In fact, are these Lagrange multipliers redefined and renamed by some constant numerical rescaling to bring everything in a canonical form, and they're still to be varied over because of the fact that when you stick this in the path integral, you're still integrating over lambda and kappa. They don't have local degrees of freedom, which is guaranteed by the presence of these new terms in the bulk, okay, of the action, which, however, are purely topological in the sense that they're completely independent of root. Okay. Now these terms violate most strongly the equivalence principle, but they violate the equivalence principle for constants. Who cares? In fact, actually, you're familiar with these guys. This is nothing new. If you write down the standard axiom dimension 5 operator, phi ff star, okay, it is precisely of this form. Actually, this is why I'm calling this non-analogous strong QCD, you know, theta QCD, strong TP theta QCD. If you write this, if you think about ff star is E dot B, okay? E dot B is a total derivative. In fact, you can write it down as a total derivative of a certain 3-form potential, and then declare it to be precisely this. Except that for a U1, it doesn't have the non-trivial topological structure. The vacuum don't have a non-trivial topological structure. You don't have a non-trivial, you know, theta parameter associated with a simple U1 on a simply connected manifold. You have to complicate the topology, but you can do the similar thing for SU2 or for SU3 or for whatever. Okay. So basically, these topological sectors, okay, are locally enforcing the constancy of lambda and kappa, you know, projecting out local fluctuation. But when coupled with the membranes, they actually generate, when you write down the equations for lambda and for kappa, you will find that via this term and the fact that the charge mixes with A, okay, you indeed get the equations for lambda and kappa, which tell you that their derivative is 0 except on the membrane where that you can jump by the amount of Q. Now, here I'm gonna now simplify the framework for the purpose of this talk. You can find the details that are going to be skipped in this presentation in the papers. Basically, I'll just give you a very brief, okay, reason for what's going on here, or rather description of what's going on here. The trick is that if you allow kappa square to vary by discrete jumps, kappa square can go both up and down. In principle, if kappa square continues going down in some sequence of nucleations and discharges, you should worry that kappa square could actually become negative. If kappa square becomes negative, that means that your theory suddenly has massless spin 2 ghosts. That doesn't sound like a healthy situation. So you want to go through some effort of getting rid of those ghosts and making sure that, you know, at least the theory can avoid this problem. And there is a formulation of theory with these couplings, but in fact the problem is completely void. Okay, those details are in the paper. I couldn't find a general proof, but I found a proof for a special version, sufficiently broad special version of the theory for which this is completely safe.
So is that, should I think of that as a version of the theory, or just
Limit.
that the theory truly doesn't actually have that behavior, even though it naively does?
Yeah, I don't know. Okay, the thing is, there are some additional details you have to worry about, and so on and so forth. I simply decided to not worry about the most general formulation, but actually the most general formulation of these couplings at the tree level and so on and so forth might not even be justified because it might not be stable under loop corrections and so on and so forth. But what I can tell you is the following, that out of the two limits which are completely consistent perturbatively and are in fact stable under the loop corrections, and by that I mean retain their form as does, remain on the same form as the classical action. Okay, one of those two is in fact guaranteed not to suffer from the invocation of ghosts. Okay, in other words, ghosts are completely under control. They live in some other universe, and you never know that. I'm gonna skip that because of the fact that for the purpose of conveying the message I want to convey, that's not necessary. That basically means I'm going to decouple kappa square dynamics, essentially fixing kappa square to be equal to a constant. It never changes. I do that by decoupling the membranes, essentially taking the tension of the membrane that could change kappa square to infinity. This is the same thing morally as taking electron's mass limit to infinity, in which case you would, in ordinary electromagnetism, be stuck with constant electromagnetic field only. Okay. So now, with this simplification, we go on and we study. Okay, what happens with what remains in the theory, and in particular how it affects Lambda. The idea is to study the Euclidean formulation of the theory. So take the action, Euclideanize it, look for maximally symmetric configurations that can lead to transitions of the geometry being solved by cosmological constants. The reason is that those extremize the action, and because of the fact that you are working essentially in what is Coleman's old formalism of bubble nucleation that mediate geometric transitions by changing cosmological constant. In his case, for some types of potentials that have a bunch of vacua. In this particular case, because of the fact that you have some background value of lambda that you can then discharge by membrane nucleation. Okay, you want to construct basically these configurations which correspond to transitions being sourced by membrane being injected somewhere out of the vacuum. Okay, and calculate what the bounce actions are. Okay, and in turn their exponents are the decay rates, and that will tell you what happens with the cosmological constant to start with. And I'll tell you.
I don't understand the time dependence. If you have a free brane, its world volume fills all of space-time. So where is something changing?
It changes. I'll draw you a diagram later.
Okay.
Okay. I'll draw you a diagram later. This is the trick about the fact that basically the way you're describing the transition here is after you write down the Euclidean configurations that mediate transition in the space changing cosmological constant. Time dependence comes after Lorentzian continuation. Okay. You can also think about it this way. It's literally like bubbles forming in a pot full of boiling water. Okay, you have a homogeneous, medium. Okay, which is your body of water being heated. Think about how it starts to bubble. Okay, before you hit the critical point. You have a very rare production of a couple of bubbles throughout the volume of water that simply randomly pop in. Okay, and then they expand. The expansion of these bubbles, okay, under the pressure of that steam inside the bubble is what leads to your time evolution. What I'm describing here with the Euclidean transition is that process that precedes that time evolution that follows after the bubble has nucleated. Okay. So I'll also point out here the differences between what I find here. There are dramatic differences thanks to the fact that it's a different formulation of the theory from Brown Teitelbaum. And as a bottom line, I'll argue that actually, well, I'll show you that in this formulation, the system space is unstable and it wants to decay to Minkowski, okay? Which means that the almost flat space is an accumulation point, okay? So here is how you solve these equations. It's actually quite simple, okay? I'm writing these equations, but I don't even want to discuss them. This is pretty straightforward. You know, bulk equation, this is what all the Einstein's equations after Euclideanization of the geometry reduce down to. That's just Euclidean Friedman equation that you write down. You're solving essentially on spheres or horospheres, depending on the sign of the net cosmological constant. These are more interesting. These are the two junction conditions. You're imposing, of course, the fact that on the transition geometry is smooth. Okay, there is no jumps in the metric itself, but there may be jumps in the first derivatives of the metric because of the fact that the membranes behave like delta function sources for in the equations of motion. Okay, and I'm not bothering to write down the boundary conditions for the three forms, which are non-trivial, but actually what happens is when you're calculating the bounce action, they completely cancel out between jumps in the three forms and the presence of the delta function sources such as the tensions in the membrane. Let me tell you what this amounts to. Euclidean de Sitter space is a sphere. Okay? If you take the Sitter space and you Euclideanize it by performing Greek rotation with time variable, and you go to global coordinates, you find it's a sphere. It's S4. Euclidean anti-de Sitter sphere is something called a horosphere. What it is a four-dimensional variant of the Lobachevsky space, okay? Or that thing that you've seen with, you know, angels on the head of the pin by Escher and so on and so forth, okay? Where you find out that as you go farther from any local center that you choose to be your reference rest frame, okay? And go away from there, most of the volume lives far, okay? To describe the transition of a de Sitter space to another de Sitter space, or maybe anti-de Sitter space, okay? What you need to do is you need to pick your initial space, which is some initial sphere. Then you chop off a slice of that sphere, which is continuing to be maximally symmetric, okay? And then you glue on top of it, okay, a space that you want this to transition into, or check whether it can transition into, which is allowed as long as the junction conditions are properly solved. Okay? So let's do this example of brain surgery in practice. Okay? So what you do, here is your starting de Sitter space. Notice that I'm taking the starting de Sitter space to have a smaller radius. Small radius means larger initial cosmological constant. Okay, I want to see whether and how it can transition, okay, to a space which via bubble nucleation, okay, which inside the bubble, okay, is described locally by a geometry which is a section of a larger sphere, meaning the Sitter space with a smaller cosmological constant. And I can construct this solution as long as in the following sense, okay? What I do is I start with my initial de Sitter space. Let's say I start from the North Pole. Then I start going away from the North Pole and pick some latitude line, speaking literally, geographically, okay? Along which I slice the sphere, okay? And I can do that as long as I can fit the perimeter of the latitude line to be exactly equal, okay, to the perimeter of the membrane I want to fit right there on that boundary. Okay. And then similarly, I go and I look for some other de Sitter space of a smaller cosmological constant, okay, also go and choose a latitude line. It's going to be at a different latitude in a new de Sitter space, but the important point is that it needs to have the same perimeter as the perimeter of this excision here, such that I can glue the two together smoothly. The two boundary conditions which control which possible transitions here can occur and which cannot occur come from the fact that in these boundary conditions, okay, I have two of them, tension and charge. This controls how much the cosmological constant changes from the parent de Sitter space to the offspring de Sitter space. And this one controls basically the perimeter of the membrane along which the parent and the offspring can be connected. The fact that there is two boundary conditions actually, for example, tell me here, you see this angle here, okay, that tells you essentially of the correlation of the two surfaces that you're gluing together. That angle has to be acute because of the fact that I'm choosing the tension to be positive. I'm choosing the tension to be positive to avoid any problems with local instability. Okay, so you can't glue it like this. This is prohibited because it would require a negative tension on the boundary membrane. Okay, the other boundary condition, given the initial values of the two cosmological constants, controls whether when I start from the North Pole, I will have to excite before I cross the equator or after. Okay, those are the two options, two boundary conditions. That's essentially what they fix. The crucial thing here, and this is what I stress, when you rewrite those junction conditions, okay, I wrote them here. You have to do some tedious algebra, and you got to make sure, you know, you got to do it a couple of times to get it right, but it's okay. The point is that this term in parentheses plays a crucial role. Okay, the term in the parentheses here, okay, is purely controlled by the ratio. I mean, this is Planck scale. Okay, so let's say it's fixed. This is completely, totally controlled by the ratio of charge to tension squared. Okay, when this is big, when this number is bigger than unity, for one of these signs, depending on the sign, obviously, the charge that you're playing with, for one of these signs, this term in parentheses will by absolute value be bigger than 1. Okay. If, however, this term is smaller than unity, the term in the parentheses is never bigger than 1, meaning that it retains the same sign. Okay. Now, this doesn't happen in the cases when you study other setups which employ membrane discharge as a way to relax the cosmological constant. Because, for example, in generic Brown Teitelbaum type constructions, and also others, people like Busso-Polchinski use these, and Wilczek and Kaloper, I mean, you know, a whole lot of people. Okay. What happens in this term is that instead of the Planck scale to the fourth piece here, okay, which comes from the fact that I have that bilinear mixing of the two forms, okay, you have a 1 power of Planck squared, Planck scale squared, and 1 power of the background flux. And that background flux changes from value of the cosmological constant that you start with, that you want to relax from one to another. Okay. So that in principle, okay, this term can be of either sign generically. In this construction, thanks to the fact that you have these bilinear pieces, or for that matter, even if you generalize by adding additional pieces like quadratic pieces and so on, as long as the bilinear pieces dominate, okay, you can pick the charge to tension ratio, okay, such that this term always retains the same sign. As a result, okay, this puts strong constraint on what instantons are allowed as ways of mediating the transitions between cosmological constants, and make very different predictions as a consequence. So I'm not, you know, that basically means generically, in the case, let's say, when you have typical F-squared type relaxations and so on, these are the allowed instances. The blank squares are the instances which are kinematically prohibited. You can't construct them because of the fact that they require negative tension. These auger type structures, which I've crossed out, actually can be kinematically constructed, but they're suppressed by infinite action as long as they mediate transitions to non-compact ADS space. You could compactify the ADS space, but that's a subleading correction. If you compactify it, make it large, the action will still be huge, will be hugely suppressed. And also they describe transitions from ADS to ADS, so I don't really care about these. Or rather, they start with initial ADS. Okay. The trick is that in this bilinear formulation, depending on that ratio of charge to tension, the transitions can only happen via these four. That's one subsector of the theory. Okay, only these four work. The other two green ones don't, or only the two green ones. There is a very dramatical consequence of that. Okay. The trick is when you calculate the bounce action, and these I've checked, I've derived this from scratch and then compared it with Coleman de Lucia and with Brown Teitelbaum, and they fit. Okay, these are the, again, you have to roll up your sleeves and compute, but okay, that can be done. The thing is this. This is the typical instanton, okay, that people encounter when they're looking at cosmological constant discharging theories that involve these Fsquare pieces. These instantons, you will recognize they're frequently the ones, well, they're the ones frequently quoted in the literature, with the actions which in the limiting form when the instanton is small relative to background curvature, and so I'll give you this expression where the bounce action goes as mentioned to the 4 divided by the cube of the difference of the two states that they connect. These instantons are fast, and moreover, their nucleation rate is roughly constant for the most part, for the most transitions which they mediate. The reason this is the case is when you construct this instanton, okay, by using the junction conditions and so on, when it is allowed, you have to remember that the bounce action is the difference of the action integrated over the volume of the instanton minus the reference action, which is the action of the configuration where you only have the parent geometry. This means that if you compare these two, the integration over this exterior piece completely cancels out between the instanton that mediates transition and the parent geometry that involves basically the full geometry without this bubble in whose interior is the de Sitter space with a smaller cosmological zone. Okay. As a result, you get the action which essentially involves contributions over only this section for both the parent and the offspring. This means that this is the reason why, in fact, this action here, importantly, will be independent of the properties of the parent geometry. Okay, because it got cancelled out. In the case these guys are prohibited by my boundary conditions, by my junction conditions, and by choice of tension or of charge to tension ratio, I'm only allowed to use these to describe transitions from the Sitter to the Sitter. Here in this case, see the same construction where I take the integral over the area of the instanton that mediates transition minus the parent action which is integrated. Only this piece that features here, its contribution cancels out between the two integrals. It leaves you with the integral over the offspring and the integral over the complement of the geometry that remains for the parent. And because that contains this big piece, this big balloon, okay, it leaves you with a contribution to the action which remembers what the parent's cosmological constant was. This action actually, and by the way, is nothing else but just the expression for the Bekenstein-Hawking entropy, okay, of the background parent space. Okay, the way to do it, to see it mathematically, okay, comes when you actually start writing all these integrals. And basically the trick is here. Basically what happens is that when these, for the instantons are this called the fast ones, these coefficients, that they tell you whether you are cutting below the geometry below you, sorry, before you cross the equator or after. If you do it before you cross the equator, these are plus. When you look at these plus signs, then you will actually find out, and you do the expansion and so on, you will find out that the cosmological constant cancels. If you go to the other instanton, these flip their sign into minus. If that's what happens for the minus guys, you will actually find out that the cosmological constant current leading order does not cancel and leaves you with this.
So can you explain here, if you think that the other formula is, at least from the point of view of constant, like an inverse of the first formula? There is kappa in the numerator, then it's in the denominator, the tau denominator, numerator.
Never mind this. This just follows when you substitute the junction conditions in there.
Okay.
Okay.
The kappa is not small or big or.
It's just M1. Okay.
The unit kind of doesn't matter.
Yeah, you see the units are okay. The tension has dimension 3. Okay. So the charge has dimension 2 because these are membranes. So the units are okay. The numerical values actually depend on, you can in principle make these too fast if you choose the charges to be bad and so on and so forth. Okay, but you can choose them to be what you like to do in the leading order. There is no prohibition to what they can be a priori. Okay, if you want, you may worry about things like gravity conjecture and so on and so forth. But let's not go there. I'll just tell you that to leading order, that's not a concern. It can be met. I just kind of I shouldn't have even put that in here. This action is the familiar one. This simply follows from the relation between delta lambda and kappa and q. But the important point is this guy, this 1 over lambda in the denominator. Why? Because notice, if you start thinking about the transitions that initiate in a parent de Sitter space, which has a very small cosmological constant, its transition rate to one with a, let's say, smaller cosmological constant or a negative cosmological constant will involve the action, which will be huge. Because the decay rate is e to the minus this action. This means that the decay rate of a space whose cosmological constant is initially small will be incredibly slow. Okay? That doesn't happen here.
I figured out what I'm confused about.
Yes?
When you introduced the branes, they were, sources for the fields.
Yes?
So I imagine they have some world sheets or whatever. But now they're instantons, not particles.
Correct.
How did that happen?
Euclidean weak rotation is precisely what does that for you. Okay. And we can talk about, the details, but basically when you perform the weak rotation, okay, this is, I don't see how that's actually really any different than what you would do when you, for example, weak rotated from Minkowski space to Euclidean space with just charges and particles. You will just get a whole bunch of stationary sources.
Right, the ADS space also decay to the concrete space.
It can, if you find an instanton that it can decay up. Certainly, all these processes are a priori allowed.
Okay.
Their decay rate is what distinguishes whether they're likely or not. Okay. It turns out that the decay from cosmological constant, which is large, de Sitter, to cosmological constant, which is small, de Sitter, is the most likely process. Okay. If you start with it, but I'll actually show you what it depends on this taxonomy of the instantons which are allowed and which are not allowed. But in principle, yes, this is not prohibited.
When you say decay rate fast or slow, how do you
I'm sorry, say again?
When you say decay rate,
Yes.
fast or slow, what do you calculate?
Okay, again, okay. By fast, I simply mean the one that stays the same for however small a cosmological constant the initial value in the initial space has. Okay, this one is fast in the sense that if you start with cosmological constant, which is epsilon, it will take you in some finite time from epsilon to minus epsilon. Okay. With this one, if you start with cosmological constant, which is epsilon, it will take an infinite amount of time. In fact, it will take an amount of time that goes e to the 1 over epsilon, okay, to change it to minus epsilon. In fact, I didn't invent these. These are these types of configurations you'll find if you very carefully read and translate the formulas in Coleman-de Lucia. Okay, in Coleman-de Lucia, this example is actually analyzed when they consider the transition from a slightly positive cosmological constant to 0 or slightly negative cosmological constant, and talk about gravitational stabilization of the initial vacuum. Okay, so this is the one. This, on the other hand, is what they use to describe the transitions for, say, spaces that have large cosmological constant initially and slightly smaller cosmological constant and so on, where the gravitational effects are negligible. But in general theory, they all mix together. You can't keep them separate. In this thing, amazingly, okay, because of the presence of that bilinear term that dominates over everything else, you separate them. You will only have these and or these, depending on how you adjust the charges to tension. Notice here I'm actually only describing for you the limiting form of the bounce action when lambda is already smaller than this Planckian term. If you take lambda initial or out, okay, to be initially comparable to this, you have to take a different form of the action, which I'm ignoring here. The details are in the papers. If you're interested in the details, you're welcome to consult the papers, which I referenced in the first page. And if there is any additional questions, I'm more than happy to answer. Okay. But the bottom line is, in this process of discharge mediated by these instances, you first start with bounce actions, which will initially be negative when lambda is very big. Okay, this means that those spaces with huge cosmological constant will actually decay to spaces with smaller cosmological constants initially very quickly. These processes will continue onward until the tension term beats the contribution to the size of the membrane that comes from the background cosmological constant, because there is a competition between them. You may remember actually in Coleman-de Lucia, when Coleman is describing when the instanton is possible, he's using a cell bubble analogy. He says what you do is you take a space that has a certain latent heat, then you remove a section of that space with that latent heat, replace it with a space that has a different latent heat, and then he says you can do this and construct this transition if the difference in the latent heats is sufficient to pay the price of producing the membrane, because of the fact that the membrane has a tension. Okay, and you have to pay the energy for it. So the same story, literally, applies here. Okay, so basically then, once you have gotten rid of most of the cosmological constant, come down to the value controlled by the tension, then the dynamic slows down and gets into the regime where actually this action controls. And so this one is the one I call slow, because it gets progressively smaller as you get closer to zero.
Do you measure in Planck time or what?
If you measure in Planck time, well, again, sure, the measure is given by the normalization of the decay rate of the prefactor that you can calculate in WKB, and it's known. So it's Planck time or the initial Hubble time, it doesn't matter. Okay. None of them are really fast. They are not one they're order one in Planck time when the initial cosmological constant is order one in Planck units. As it has discharged to smaller values, they're all slow, but this one is heck of a lot slower because of that 1 over lambda number. Here is how it solves the problem. So when you start collecting all of the terms that you have that contribute to the cosmological constant, okay, This is what you get from your field theory. Okay, the whatever, you know, the UV contributions being dominated by the quartic power of the cutoff, some potential, and of course this is disintegration constant. Disintegration constant, okay, may have some classical integration constant contribution, plus of course the flux generated by the charges that source it. So the net cosmological constant the theory has is all of these terms, they combine together, plus the fluxes. Okay. Now, the problem with this is that here is what the problem is. This can only lead to a net small cosmological constant after some number of n discharges. Either if you take the charge to be absolutely tiny, you know, teeny tiny puny, okay, epsilon, all right, or you fine tune the initial value of the net cosmological constant that you started with to be within a small value of, you know, some n times the unit of charge, okay. And incidentally, Brown and Teitel, in their 1988 paper, for this reason, take the charge to be 10 to the minus 120 m-Planck squared. Okay, that is not the solution of the cosmological constant. That's the problem. Okay.
So can you explain, so in that case, you could say that the first time is zero, or you would like
Now let me explain it using this plot. Okay. This formula that I've just given here.
but these are two positive numbers, something can be negative. It can be negative.
No, certainly it can be negative. N can be either plus or minus. You're either emitting charge or absorbing charge, for example.
So you can have cancellation.
That's the whole point. But that cancellation is not enough for the following reason. Okay. By itself, I'll tell you what extra step needs to be made. The trick is that if you start with some initial value of lambda naught from the previous slide, as you're emitting membranes, that lambda naught can change, okay, in steps given by the integer number of units of charge, okay? And it can continue until you fall into the anti-de Sitter territory. And then, of course, if you fall into the anti-de Sitter territory, then this stabilization mechanism of Coleman will arrest it and the evolution will stop. Okay. The point is that these different sets of sequences are in fact like super selection sectors, parameterized by the initial value of lambda naught. Okay, they don't mix. You're changing every time you nucleate a membrane, you change lambda by 1 unit of Q naught, whatever you started with. Okay, so if you want to get arbitrarily close to 0 to within 10 to the minus 120, either you have to choose a special tower whose initial value was given by 10 to the minus 120 plus the number of charges that you emitted, okay? Or you need to make this interval given by the charge to be absolutely tiny so that you fall in here. When you fall in here in your last step, you are within 10 to the minus 120 of 0. That's the problem. Here is the fix. It's actually straightforward. The fix goes back to this incredibly prescient paper from 91 by Banks, Dynamically, called the irrational axiom proposal, where what you do is you add one more parameter. In other words, you add one more copy of that 3-form A potential and one more copy of the charges and tensions associated. And you make it completely degenerate with the previous ones in the action with the cosmological constant. Okay. And you take the charge that controls the new jump, okay, to be related to the charge you already have by a ratio which is an irrational number. Okay. The reason you do that is that if you now consider a sequence of emissions of the two different types of membranes, okay, You're emitting the A membrane, then you're emitting A hat membrane, you're emitting A hat again, then A, and so on and so forth. If you have a long sequence of emissions, some going up, some going down, and so on, okay, you will always find a sequence that comes arbitrarily close to any real number. This is just theorems about irrational numbers in mathematics. Basically, it's the statement that the set of irrationals is dense in a set of reals. And you can always find a sequence of irrational numbers such that a real number is its accumulation point. And in particular, okay, what's going to happen is if you now have a system of emissions of both types of membranes, okay, you will find that for any lambda naught, given that this is an irrational number, there will be a system of n and n hats, okay, such that the sum total will be arbitrarily close to zero. Okay. Once you get arbitrarily close to zero, on the other hand, subsequent emissions of these membranes are going to slow down to a trickle because of the fact that either set of discharges is controlled by the same type of bounce action, because for each of them, I have chosen Q to tension to be in the right ballpark where only the good instanton that I like can mediate the processes, and what I call the fast instanton is kinematically excluded. So now you basically have two things that happen, okay? All of these, you see, these formerly super selection sectors, which were separated when you have only one type of membranes, are now mixed. You can jump from here to here to here to here to here to here, anywhere where you want, by the fact that there exists a quantum path of these random discharges, okay, that will take you to the right value. Moreover, because of the fact that the emission rate has an essential singularity, given that the bounce action has a pole at zero, okay, they will accumulate here. Some may jump on the, okay, too bad. You will end up in anti-de Sitter universe in which you cannot live. But most of them won't do that because of the fact that they will want to accumulate right around zero. Okay? Why? Because if they jump up here, they can actually fix things by jumping back up. This is going to be a very rare process, but in a universe where this is repeating and repeating and repeating, inevitably, okay, these processes that don't tend will win.
Nemanja?
Yes.
I'm waiting for the right moment to ask a question about the arrow of time. This might be it.
I have thoughts about it. Don't ask me quite yet.
Okay.
Because
I do have to run to my appointment.
Yes,
so
I will.
Maybe we'll catch up later. Okay, because it's
I
there, it's somehow there, and yet.
I think it may be there.
Yeah.
I think it may be there.
In these.
Yes.
This history you're describing, it's there.
I came this close to writing about this in these papers as well, but then I decided that maybe this deserves a separate.
That's fine. I mean, the tradition is not to worry about it.
No, yeah, I'd like to get a more complete story.
Yeah. So let's talk about it.
Right. So what as a result of this evolution, you see, the thing is you're adjusting by quantum drift, not by classical drift.
Mm-hmm.
So you get a chance to correct. You occasionally go up and then you repeat and you keep going down and so on and so forth. Except that once you get in the right ballpark, which is the cosmological constant is close to zero, then the emissions just stop because it's a natural attractor. And the theory just tells you, oh, don't bother doing this anymore. You don't need to. You're where you want to be, so everything is cool. Basically, the miracle of this is that, this essentially ends up realizing effectively this old proposal of Baum and Hawking from 1984, who argue based on the Euclidean quantum cosmology, okay, that the most likely value of the cosmological constant is zero, essentially by taking Hartle-Hawking's wave function and declaring it to be the measure of likelihood of the value of the cosmological constant in a liquid. The one thing that they never did have here, they wrote down the Euclidean wave function and the Euclidean partition function, which is supposed to count something, but they didn't know what they were counting. What I'm arguing here is actually that this is in fact counting precisely the dynamics of transitions mediated by these membranes in the regime where the bilinear term dominates over everything else. When you choose the tension and the charge to be right, meaning that the charge is slightly, well, in the units of appropriate units of Planck scale, charge is slightly smaller than the tension square. So as a result, you end up with this conclusion. It's inescapable that you're basically getting driven towards lambda equal to 0 by quantum dynamics. Why this is happening? Here is the heuristic description of where that bilinear term changes the story relative to quadratic pieces. This is, for example, Brown, Teitelboim, or Busso-Polchinski, and so on and so forth. In those setups, the net cosmological constant you're trying to relax is essentially dependent quadratically. In fact, I should have put it minus here and plus there. Forgive me, okay? This should be really minus and plus, okay? The cosmological constant you're canceling, okay, is a parabola in charges. Charge is quantized, so in fact, actually, this parabola is not continuous. It just has a discrete set of numbers. Which of these two instances you use is controlled by the slope of the tangent at any particular point on the parabola, which describes the initial cosmological constant you want to cancel. If the slope is steep, you are forced to use for transition by the boundary conditions those instances that lead to the transitions which do not depend on the background value of cosmological constant. And you never stabilize that space. You always go, when you your jump, you can always make another jump and continue going down, okay, until that is you get to the very end. But even if you quantize in the units of large charge, you'll never get down here because of the fact that there is no points that you can occupy. But in the bilinear case, this slope is fixed because of the fact that cosmological constant depends linearly on charge. So for all values of cosmological constant, the transition rate is the same. Okay, and you can, choosing the slope once, you fix it forever, and then you're driven towards this value as the accumulation point where the action just builds up and the rate goes to 0. What this may remind you of is the old story of Abbott from 1985. Abbott has constructed an adjustment mechanism that involved a field rolling down a linear potential and canceling the cosmological constant. And by the way, this reminds you of a figure from the relaxion, it should, because I stole it from the paper. Okay, the trick is that once you see, you get down here, you get trapped by these, this is equal to 0 and so on, okay? But in order to get to this point, you need to be in constant slow roll all the way down here, meaning that the universe that this fills up is constantly inflating. Until that is, the value of this field gets close to where the energy density is equal to 0. But that leads to the so-called empty universe problem because of the fact that by the time this all ends and you reheat to temperatures given by the current Hubble parameter 10 to the minus whatever, 33 electron volts or whatever it is. Okay, in other words, you never reheat. In this case, this is avoided because you're not constantly slowly rolling. You're jumping up, down, and then you hit the right spot and it stops. And in between that time, between the last jump, okay, and now you have in principle a possibility for a long epoch where you can fit normal 60 phosphorylation, normal reheating, normal BBN, and so on. So you avoid the problem by basically Brownian drift. This I've just said it, so let me not dwell on that any further. Now this I don't know. Okay, what by this argument I'm making, whatever drives the evolution now is not the cosmological constant. I tried thinking a little bit about it, but the problem is if you take a cosmological constant which is small, and you compare it with the situation where the cosmological constant is even smaller, okay, the ratio likelihood, okay, of there being the larger cosmological constant, which is not equal to 0 and can go to 0 via this mechanism, is given by e to the -1 over the smaller cosmological constant, which is exponentially over volume. So it seems it's exponentially unlikely. It could be transient quintessence, okay, it's a cop-out, so I'm just kind of throwing it in there. Maybe late stage phase transition, something like what we have done with strong CP, that might then invoke anthropics, but just for the explanation of the late phase of acceleration. I don't know. Maybe that ratio of charges, that irrational number that I mentioned is actually not irrational. Maybe it's a rational number, but it's a ratio of, you know, two huge numbers that are mutually private, so that it's 10 to the -120. I like that. I like that very much, but I can't calculate that. Or maybe there is some other, you know, reasoning about likelihoods and probabilities that comes up when you try to fit inflation in. I don't know that. That's open. So just to kind of summarize, okay, what's the message? I guess to me, at least, the main message is, in some sense, there really is infinitely many GRs. And maybe not only GR parameters are the ones that should be, you know, viewed as this discrete variable that can vary over this. I like to call this pan-cosmic landscape, pan-cosmic relativity, okay, as in super cosmic. Maybe it's also the Higgs mass. And maybe in principle, you can have some kind of a setup where dynamically you generate hierarchies through this random quantum dynamics in this big space. It's very simple. It's just GRs. You don't need in principle, you don't really need to have some very complicated, sophisticated ingredients from string constructions and so on and so forth. It's been always kind of there, tapping you on the shoulder and saying, "Hi, I'm here, see me." Without introduction of membranes, these are integration constants you can fix and forget. Okay, but if you have dynamics whereby they can change, then you get some interesting possibilities to consider. One of those is the recognition that the Sitter space is actually, it's non-perturbatively unstable. It is stable perturbatively. It satisfies the Bianchi identities and so on, but non-perturbatively, it's unstable to this membrane creation, where a membrane can pop out quantum mechanically. And John was asking, actually, I promised I was going to draw the Lorentzian continuation. So you take these guys that I drew, okay? You turn them upside down, you cut them where they're thickest, and then you do the Lorentzian continuation where you recrotate one of the angles, promote it into the time. From here on, you have expanding the Sitter space parent, which is expanding with a big cosmological constant. You have inside that the Sitter space a bubble whose walls are also expanding super exponentially, whose internal geometry is de Sitter as well. And in the interior of the wall, you have another de Sitter, okay, which is expanding exponentially, but at a slower rate because its cosmological constant is smaller. The good thing is that this thing wants to decay towards Minkowski. No anthropics is needed. One discrete choice of ratio of charges to tensions, and I'm done. Okay. The other good thing is that the decay rate is controllably slow. So that even though you're getting rid of the Sitter, you may be able to get rid of it slowly enough so that you can have inflation. Okay. Some of these other problems that people, like these so-called Boltzmann brains and so on and so forth, that can be averted because of the fact that you're eventually being led towards Minkowski as an attractor, and so the number of degrees of freedom gets large, and Boltzmann brain type fluctuations get suppressed relative to stuff that goes normal and shut. You can also have a possibility of restarting the universe quantum mechanical. You have some sort of small cosmological constant, and then in some very rare process, a priori very rare process, it jumps to some large volume. That's possible, okay? And then you get a second chance. So as long as you haven't gotten rid of cosmological constant completely, you can choose it to, you know, retry again. Okay. So obviously there are many other questions and so on and so forth, but let me stop here instead of speculating loudly too much.
Questions?
What's the Euler competition in finding proper quantum gravity?
I wonder. But this is something, it hasn't been explored much, okay? So I did mention I had a, you see, what I'm thinking about is that maybe this, there is a way of actually understanding something like this without really even needing some sophisticated quantum gravity. But imagining that you start with some strongly coupled gauge theory that has its own non-trivial theta parameter. In perturbation theory, all the theta parameters are, all the theta vacuum are energetically degenerate. But we know from that old Waffa-Witten theta from 87 or something, that when you turn on strong coupling and non-perturbative corrections, degeneracies are broken. Different thetas correspond to vacua with different vacuum energies. I'm literally thinking of that lambda, okay, to be actually an energy associated with some theta vacua. The transition between different theta vacua will happen via something like, you know, actually bubbles that are changing the topology by changing the winding number, okay, in some thin wall limit, okay. These bubbles will look like membranes. So now there will be actually a tower of possible transitions inside these theories, you know, strongly coupled. I don't know, it goes strongly coupled at a gut scale or something like that. Below the gut, something, you know, something fixes cosmological constant above the gut scale. Okay, I don't know what that is, but below the gut scale, it's the topology of the strongly coupled gauge theory that picks up the slack and adjusts the rest to zero, essentially selecting its own, you know, ground state. That, of course, one theory isn't enough. I need to have at least two theories with the charges being mutually rational, but then that's it.
Can you skip a slide annexation or
Again,
you just skip a slide annexation?
yeah, because I thought I mentioned it in words, but we can go back to it. Right. Here is the slide. The idea in this slide was simply to say nothing specific per se, but merely the fact that, you know, you can finish the adjustment of cosmological construct to tiny volume while the universe is still young. And after that last jump, you can still end up having, at least in principle, some 60 epochs of inflation that you need to fit the phenomenological requirements, such as nearly flat spatial slices and you know, produce the right spectrum of fluctuations.
So say you already adjust the cosmological to zero.
I need to model build to do that.
Before the inflation ends?
Yes, this, for example, this is the same idea that's in Busopoczynski. Same idea that's in Wilczek, Sethi, Russell, etc. Yes, you need to model build it. One to be completely frank with you, I mean, this might be where you might even have to go back towards anthropics, maybe. I'm not sure.
Usually one of the problems that how do you know which part is the cosmological
I know.
constant, which part is the ordinary damage? How do you know what to cancel that one?
Let me put it this way. In the previous attempts to address those same questions, they didn't even have the special value of this attractor, the quantum attractor of zero. So now I have at least found that there is a variant of the theory where you get a quantum attractor which selects lambda equal to zero as a special part. So now I want to see whether that's going to give me a different way to address the question about what that late cosmological constant should be. That's the best I can tell you right now. There are people, by the way, who even say it may be possible to cancel the cosmological constant to zero non-anthropically. But to explain why it is not exactly equal to zero, you may have to do anthropics. I don't know, okay?
But in principle, you didn't really, you just say it's a tracker point. It doesn't really set it to zero, right? It doesn't have a much bigger probability.
Absolutely, but it has exponentially bigger.
Mm.
So it is exponentially unlikely not to. Okay, if it were only a power law, I would be less optimistic about this. But because it's exponential with an essential point singularity, okay, in the decay rate, it really likes it. There is a way, okay, to actually try to verify this with more details. In principle, you can try to calculate the more detailed distribution of values using something called stochastic inflation formulation or eternal inflation, which this is a special example of, okay? Except that this should be simpler because of the fact that transitions are only of one kind. You don't have to worry about starting with some random potential and so on. You have a cosmological constant, you have these steps, and you sit down and calculate. So that's obviously a project I want to do.
So given the vacuum energy before the electroweak phase transition, how long should it have had that vacuum energy?
I don't know. We'll think about it together. Obviously, an interesting question.
And how long should it have the current vacuum energy?
The current vacuum energy, if it's, you can estimate from these, in fact, actually, that current vacuum energy, there is a number in Abbott. In the very end of the paper, like 5 lines before the end, there is a statement of e to the 10 to the, I don't remember, okay? I think e to the 10 to the 101. Okay, so very long. But there was also some specific assumption about what channel you have available to you to change it, that you may have to, reanalyze here once you pick the numbers.
Okay, well, let's thank Nemanja again.